Hi, welcome back to Number Properties. In this lesson, we study factors and multiples. Then we look at the most important numbers there are, the prime numbers. We see how every number can be factorized into primes and in a unique fashion. That's called the unique factorization into primes. And then we look at several problems involving these concepts. So let's begin with factors and multiples. There's a lot of confusion among people about what is a factor and what is a multiple. Well, that's just a word. So let's see, what is the factorization of a number? So say I have a number 14. I can write 14 as 2 into 7. Or I can write 14 as 1 into 14. These are both factorizations of the number 14. 14 has been written as a product of two or more numbers. So that's a factorization of the number. And 2 and 7 are called its factors. 2 and 7 are factors of 14. The factor of a number is a number that properly divides another number. For instance, 14 divided by 2, we get a quotient of 7 and a remainder of 0. So whenever the remainder is 0, the number properly divides, and so it's a factor. That's the meaning of factor, that the remainder on division is 0. What's a multiple? Well, a multiple is the opposite. If 2 and 7 are factors of 14, then 14 is a multiple of 2 and 14 is a multiple of 7. Multiples are larger numbers. So the multiples of 3, for instance, will be 3, 6, 9, 12, and so on. So multiples are those numbers which are evenly divided by the given number. So the multiples of 5, for instance, are 5, 10, 25, 105, 2000, because all these numbers are divided by 5 with remainder 0. And 5 is a factor of all these numbers because 5 divides each of these numbers. If the sum of the divisors of a positive integer n is twice of n, n is. So well, remember that divisor is a synonym for factor. So the question could have been worded, if the sum of the factors of a positive integer n is twice of n, n is. Let's try the first number 6. Let me list all its factors or all its divisors. So the best way to list all its factors is to write it as a product of its factors. So 6 can be written as 1 times 6 or as 2 times 3. So it has 4 factors. The factors of 6 are 1, 2, 3 and 6. No other number divides it properly. What is the sum of these factors? The sum of these factors is 12. So, if the sum of the divisors of a positive integer n is twice of n, then n is 6. Yes, so the sum of the factors is 12, which is twice of 6. So, 1 certainly satisfies the conditions. How about 8? What are the factors of 8? 8 can be written as 1 times 8, 2 times 4. So again, there are 4 factors. 1, 2, 4 and 8. What is the sum of the factors? The sum of the factors is 15. Are the sum of the factors twice the number? No, 15 is not twice 8. So 2 is out. How about 3? 28. What are the factors of 28? Let's list them. 1 into 28, 2 into 14, 4 into 7. And nothing more. 7 4s are 28, and there's nothing more than 4 and less than 7 that divides 28. The factors of 28 are 1, 2, 4, 7, 14, 28. And the sum is 14 plus 7 plus 7 is 28 plus 28, 56. So 56 is 28 times 2. So 3 again, 28 is a valid number. So both 1, that is 6, and 3, that is 28 work. And the answer is E. So having looked at factors, let's look at the most basic factors that any number can have. Those are the prime factors. So what's a prime number? Prime number is a positive integer that has only two factors, 1 and itself. Well, every number has to have these two factors, 1 and itself. For instance, any number n can always be written as 1 into n. So it will always have these two factors. The special thing about a prime number is that it has no other factors apart from 1 and n. Well, we all know some of the prime numbers. 1, firstly, is not a prime number. Let's just get that out of the way. It's a convention. We don't want 1 to be prime. So let's start with the primes. 2, 3, 5, 7, 11, 13, 17, 19, 23, and so on are the first few prime numbers. Let's notice that 2 is prime because, 1 times 2 is 2 and there's of course no other factor other than 1 and 2. But since 2 is prime, none of the multiples of 2 can be prime. So that rules out every other even number. Every other even number, 4, 6, 8, 10, 12, will be divisible by 2. So 2 is the only even prime. All other prime numbers are odd. The next number 3 is prime. Then 4 is not prime because obviously it's even. 5, 7, 9 is not prime even though 9 is odd because 9 is 3 times 3. Then 11, 13, 17, and so on. So we have a list of prime numbers that goes on forever. There's a very elegant proof that shows you that there is no largest prime. Given any prime number, there's always one more prime bigger than that. So the number of primes is infinite. Of course, we don't need to get into that proof, but you should know that fact. There are infinitely many primes. What is prime factorization? Prime factorization is expressing a number as a product of factors, all of which are prime. Let's see how we go about doing it. So let me take a number like 12. And I'll draw what is called a factor tree. So I can write 12 as 2 into 6. Well, since 2 is prime, I'm not going to break this part down further. But the 6 is not prime, so I can break it down further as 2 into 3. I have my factors now. So to build up 12, I can do 2 times 3, which is 6, further times 2, which is 12. So 12 is 2 times 2 times 3. This is the prime factorization of 12. There are 2 2's and a 3. In exponent notation, I can write it as 2 square times 3. So I'll always write my prime factorization as a product of powers of primes. Let's see another example. How about something bigger like, say, 50? Again, 50 can go as 2 into 25. I want to quickly get to the primes. And 25 I know is 5 times 5. So here again I have my prime factorization pretty rapidly. It's 2 times 5 square. Unique factorization into primes. This is one of the most beautiful theorems in number theory. What it says is not only that every number can be broken down into primes, which is obvious because either a number is prime or it is not prime. If it's not prime, it has a factor which is lower than itself. So express it as those factors and carry on the argument till you touch a prime. And finally you will touch all primes, and that is the prime factorization of the number. So the fact that every number can be written as primes is not deep at all. It's just a consequence of multiplication and the definition of primes. What is more delightful is that it's unique. There is only one way to write every number as a product of primes. You can express it in 2 different ways. For instance, 12 was 2 square into 3. You cannot write 12 as a product of prime numbers in any other way. It will always be 2 2's and a 3. That's the uniqueness. There is only one way to write a number as a product of primes. And that's true for every number. Every integer is uniquely factorizable into primes. We'll use this fact in many problems. Let's look at a typical problem. 25 raised to x times 27 raised to y is 225 raised to 4 times 9 raised to 5. Find the value of x plus y. So I'm going to bank on my uniqueness of prime factorization. So I'm going to cut these products down into prime factors. So I'll start with 25 raised to x. 25 is 5 times 5 raised to x, which is 5 squared raised to x, which is 5 raised to 2x by the rules of exponents that we learned earlier. How about 27 raised to y? 27 raised to y is 3 times 3 times 3 raised to y, which is 3 cubed raised to y, which is 3 raised to 3y. So you see, I have my prime factorization of 25 raised to x times 27 raised to y. What is the prime factorization of the left hand side? It's 5 raised to 2x times 3 raised to 3y. I've expressed the left hand side as a product of prime powers, 5 occurring 2x times and 3 occurring 3y times. This is the prime factorization of the left hand side. Let me do the same to the right hand side. So 225 is, I'm going to break it down as 5 times 9 and 9 is 3 times 3. So the prime factorization of 225 is 3 squared times 5. Similarly, what's the prime factorization of 9? 9 is easy, it's just 3 times 3. I don't actually need to do it. So the prime factorization of 9 is 3 squared. Let's just write it. So what's the right hand side become? The right hand side becomes 3 squared into 5, the whole raised to 4 times 3 squared raised to 5. Now I can use my rules of exponents. This becomes 3 squared raised to 4 times 5 raised to 4 times 3 raised to 10. A power raised to a power, you multiply the exponents. Let me group all the powers of 3. So this becomes 3 raised to 8 into 3 raised to 10 into 5 raised to 4. This becomes 3 raised to 18 times 5 raised to 4. Because 3 raised to 8 times 3 raised to 10, you add the exponents when the bases are the same. So it's 3 raised to 18 times 5 raised to 4. Now we're pretty much done. The left hand side is expressed as a product of primes. The right hand side is expressed as the product of primes. The two sides are equal. Since we know that there's a unique factorization into primes, if there's a prime 3, then 3 should occur the same number of times in the left hand side and the right hand side, which tells me that 3y must equal 18 or y is equal to 6. The prime 5 likewise should occur the same number of times in both factorizations. On the left hand side it occurs 2x times, on the right hand side it occurs 4 times, so x is equal to 2. And so we have x is 2 and y is 6, and we can answer the question x plus y is 8. So this was a very nice example of unique factorization of primes. First, factor everything into primes, write them as prime powers and compare. So factors and multiples lead us to common factors and common multiples. What are common factors? So suppose I have two numbers, 16 and say 20. I can ask the question, what are the factors common to 16 and 20? We'll see later why this question actually has meaning. It's not just a random question. So what are the factors common to 16 and 20? Well, let me write all the factors of 16. 16, the factors are 1, 2, 4, 8 and 16. How do I know that? Well, 16 is the power of 2, so it's only divisible by 2 and its powers, which are 1, 2, 4, 8, 16. 20 is 4 into 5. So that's the factors are 1, 2, 4, 5, 10 and 20. Let's check that. 1 into 20 is 20, 2 into 10 is 20, and 4 into 5 is 20. So I have all the factor pairs. Now my question is, what are the common factors of 16 and 20? So the common factors can be read out. They are 1, 2, and 4. Those are the common factors of 16 and 20. That's the meaning of common factors. Write all the factors, pick all of them that are common. What's the highest common factor? The HCF is obviously the highest of the common factors. So in this case, it's 4. The term HCF stands for highest common factor. There is an equivalent term. It's called GCD. That's the greatest common divisor. Greatest common divisor. Because factor is the same as divisor and highest is the same as greatest. Fortunately, we don't have terms like greatest common factor and highest common divisor. We'll have 4 terms for the same thing. So we restrict ourselves to these 2. HCF equal to GCD equal to 4. The next term is common multiples. Let me take another example for common multiples. So what are common multiples? So suppose I look at the numbers 6 and 8. And I ask, what are the common multiples of 6 and 8? So firstly, I list the multiples of 6. The multiples of 6 are 6, 12, 18, 24, 30, 36, 42, and so on. What are the multiples of 8? They are 8, 16, 24, 32, 40, 48, and so on. What are the common multiples? Well, the first common multiple you'll see is 24. The next one is 48. And the next one would be 72, and so on. So those are the common multiples. The common multiples are the ones that are multiples of both 6 and 8. What is the lowest common multiple? Popularly called LCM. Well, the lowest common multiple you can see is 24. Why don't I ask what's the highest common multiple? Well, obviously there is no highest common multiple because the common multiples will go on forever and there will never be a highest common multiple. There'll always be one more. So the only sane question to ask, if at all, is what is the lowest common multiple? But simply if I were to ask you what is a common multiple, the easiest way to do it would be to multiply 6 and 8 because that is 48 and that is obviously a multiple of 6 and that is obviously a multiple of 8. So multiplying the two numbers is surely going to give you a common multiple. But that may not be the lowest common multiple. The lowest common multiple might be less than that. Like in this example, the lowest common multiple is 24 and that is not the product of 6 and 8. And that is a very important fact to keep in mind. Let's look at an example where we see the relationship between factors, highest common factors, multiples and lowest common multiples. Look at our example of 12 and 18. Just look at the numbers 12 and 18 and let's find out the highest common factor. So what are the factors of 12? 1, 2, 3, 4, 6 and 12. What are the factors of 18? 1, 2, 3, 6, 9, 18. So what is the HCF? The HCF or the GCD is 6. That's the highest common factor. What's the LCM? For the LCM, I need the multiples 12, 24, 36, 48. Factors of multiples of 18, 18, 36, and I'm done. So the LCM is 36. Let's note an interesting fact. Let's multiply the two numbers, 12 into 18. And let's multiply the HCF and the LCM, 6 into 36. Notice that these two products are equal. 12 is double of 6, while 18 is half of 36. So I know that these two products will be equal even without multiplying them out. So here's a very interesting fact. If you have two numbers, then their product is equal to the product of their HCF and their LCM. Let's look at one more example. Find the LCM and HCF of 60 and 24 using prime factorization. So let's see how factoring into primes makes this entire exercise neater. So firstly, I have to factor the numbers 60 and 24 into primes. Let's do that. Let's do our factor tree. 60 is 2 into 30. 30 is 2 into 15, and 15 is 3 into 5. So the factors of 60 are 2 square into 3 into 5. 24, 2 into 12, 12, 2 into 6, 6, 2 into 3. So 24 is 2 cube into 3. 8 into 3 for those who want to do it fast. So I have my two prime factorizations. Let's pull out the HCF. The HCF is a factor that is common to both. That means for each prime, I'll look at if that prime occurs in both, and I'll look at how many times it occurs in both. I'll take the lowest power because that is the power that occurs in both. It has to be a factor of both. So for instance, I look at prime 2. The prime 2 occurs twice in 60 and it occurs 3 times in 24. So for it to be common, I'll have to take just 2 square because that is common to both the factorization of 60 and the factorization of 24. Next, the prime 3 occurs once in 60 and once in 24. So I'll just take the prime 3 once. Next, the prime 5 occurs once in 60 but it doesn't occur in 24. So it cannot occur in the highest common factor. If I put in a 5, this number will not be a factor of 24 because 5 is not in the prime factorization of 24. So I'm done. This is the highest common factor. It's 4 into 3 equal to 12. How about the LCM? So let's rewrite the factorization of 60 and 24. 60 was 2 square into 3 into 5 and 24 was 2 cube into 3. And we just saw how to take the HCF. Let's see how we can pull out the LCM. The LCM has to be a multiple of both numbers. So it must contain the entire prime factorization of that number and maybe more. Because it has to be a multiple of this number. So I look at the first prime factor 2. It occurs twice in 60 and thrice in 24. So I'll take it 3 times. Because I need it at least 3 times for it to be a multiple of 24. Then I look at the next prime factor 3. It occurs once in each, so I need to take it only once. Then I look at the next prime factor 5. 5 occurs in 60 once and it doesn't occur in 24. So I need to take it once, otherwise this LCM will not be a multiple of 60. So I take it once and now it's a multiple of both numbers. I've covered all the primes and I've taken enough of each prime for it to be a multiple of both numbers. So we can see that the LCM is 120. So the technique for getting the HCF and LCM from prime factorization is straightforward. For the HCF, take as many primes as are common to both, and for the LCM, take primes that cover both multiples. So take a prime even if it occurs in only one of the factorization. Let's see where HCF and LCM come into play. So a teacher had 84 books and 56 erasers. He distributes all of them among the students of his class, and each student receives an equal number of books and an equal number of erasers. So if every student receives an equal number of books, that means that 84 books were given to students, and each student got an equal number of books and there was no remainder. So what can it tell me? It tells me that if n is the number of students, then n divides 84. And each student received an equal number of erasers too. So that tells me that the 56 erasers, when distributed among the students, left no remainder. So the number of students divides 56 too. So n divides both. So n is a common factor. What can be the maximum number of students? So what can be n for it to be maximum with this property? So n is the HCF. It is the maximum of the common factors, so it must be the highest common factor. So the question is basically asking what is the highest common factor of 84 and 56. Let's try to do this quickly. 84, I'll try to factor it. I know it's 4 into 21, so which is 4 into 3 into 7. I'll try to factor 56. This is 7 into 8, which is 7 into 4 into 2. So you see, I've managed to get 7 and 4 common. And I know the 3 and 2 are what's left over and they're prime, so they can never be common. So I know that 7 into 4 is the HCF, 28. 7 into 4 is the HCF. I just did some quick factorizations, not necessarily into primes, and then I pulled out stuff. So 28 is the HCF. The maximum number of students in class must be 28. Let's see if that's reasonable. If there were 28 students in class, yeah, sure, I could distribute 84 among them. Each would get 3. And yeah, I could distribute 56 erasers among them. Each would get 2. And clearly no number greater than this will divide 56 unless it's 56 itself. So 28 is the answer. The number 2544 is divisible by both 6 and 8. Which of the following is the first integer greater than 2544 that is also divisible by both 6 and 8? So if 2544 is divisible by both 6 and 8, what does it make 2544? It makes 2544 a multiple of both 6 and 8. So it's a common multiple. Which is the first integer greater than 2544, which is also a common multiple of 6 and 8. That is, which is also divisible by 6 and 8. How do the common multiples of two numbers move? Well, that's an interesting pattern. We need to first find the LCM. So what's the LCM of 6 and 8? The LCM of 6 and 8, I'll just try multiples of 8. 8, 16, 24. Yeah, 24 works. So the LCM of 6 and 8, LCM of 6 and 8 is 24. So the common multiples of 6 and 8 will all be multiples of the LCM. Remember this. Common mults of 6 and 8 are multiples of the LCM. So we've been told that 2544 is a common multiple. So we know that it's a multiple of 24. We can actually verify that. You can quickly divide 2544 by 24. 2544 divided by 24 will give me 106. So yes, it is a multiple of 24. And I know that every common multiple is a multiple of the LCM. So what's the next multiple of 24? If 2544 is a multiple, then I need to add 24 to get the next multiple. That will be 2568. That will be the next multiple of 24. And therefore, that will be the next common multiple of 6 and 8. That answer is D. How many positive integers less than 300 are divisible by both 9 and 4? So again, are divisible by both 9 and 4 means that they are common multiples of 9 and 4. So what's the LCM of 9 and 4? Well, just take all multiples of 9 till you get a number that's also a multiple of 4. 9, 18, 27, 36. Yep. 36 is a multiple of 4 and the earlier ones are not. So 36 is equal to the LCM. We know that every common multiple of 9 and 4 is a multiple of the LCM. So how many positive integers are divisible by both 9 and 4, which means are common multiples of 9 and 4. Those are the ones which are multiples of 36. So 36, 72, etc. till we reach 300. We have to go less than 300. Obviously, there'll be, if I get to 360, there will be 10 multiples. So I go 2 down, 36 and 36 down. And I'll reach 200 something. That's 72 down, so I'll reach 288. That's the last multiple, and that's the 8th multiple. So my answer is C8. How many positive integer factors does 450 have? How do I calculate all the integer factors of a number? Well, there's one brute force way. I actually list all the factors. So I take 450 and I write them in pairs. 1 times 450 or 2 times 225 or 3 times 150 or, well, 4 doesn't go in, so 5 goes in, 5 times 90 and so on. And I count each pair of factors is giving me 2 different factors in general, so I count all the factors. That's one way of getting them. Here's another way which is more foolproof. I will factor 450 into primes. So 450's prime factorization. That's 2 into 225. 225 is 5 into 45. And 45 is 5 into 9, which is 3 into 3. So the prime factorization of 450 is 2 times 3 square times 5 square. So 2 times 3 square times 5 square is the prime factorization of 450. And I want all the factors. So we know that every factor of 450 must divide 2 times 3 square times 5 square. So every factor of 450 has to involve just these 3 primes. It has to either involve 2, 3, 5 and a combination of them. How many ways can I take different combinations of 2, 3 square, 5 square? Well, for 2, I have 2 choices. I can either take the 2 or I leave out the 2. So there are 2 choices involving the prime 2. How about the prime 3? How about the prime 3? Well, it's 3 square. So I can leave out the 3. I can take 3. Or I can take 3 square. There are 3 choices for the prime 3. 3 choices. How about the prime 5? Again, I can leave out 5, I can take 5, or I can take 5 square. I of course can't take 5 cube because 5 cube will not divide 450. And these are factors of 450. So I can have 3 choices for the prime 5. And by the multiplication principle we saw in the lesson on counting, the total number of factors will be 18. 2 into 3 into 3. So that's a neat way of doing it. Factorize your number into primes. Then decide how many choices you have for each prime. So if the prime power is 2, like in 3 squared, you have 3 choices. You can either not take the number 3 or take the number 3 once or take the number 3 twice. So for each prime, depending on its power, you have that many choices. Multiply out the choices for each prime and you get the total number of factors. Let's move on to a more interesting question. How many even integers between 20 and 200 are factors of 450? We just saw how many factors 450 has. Now we want the even integers between 20 and 200 that are factors of 450. So let me again write the factorization of 450. It's 2 into 3 square into 5 squared. Now I want even integers. So remember, when I'm picking a factor of 450, I'm basically picking 3 prime numbers. I'm either picking the 2 or not, and then I'm either picking 3 square, or I'm not picking 3 at all. And then I'm either picking 5 square, or I'm not picking 5 at all. So this is the position for the 2, for the 3 and the 5. And these constitute all choices of factors of 450. Now that I want this factor to be even, I have to pick the 2. So there's only one choice here for the 2. I can't leave out the 2. So every factor of 450 will have a 2 in its prime factorization. And then I have to decide how many 3s and how many 5s I will pick. So let's look at that. So I pick the 2, which is forced. Now the position of the 3s and the positions of the 5s. Now it has to be greater than 20. Well, greater than equal to 20. So I can't just take a 3 because 2 into 3 is 6 and that's less than 20. And I can't just take a 3 square because that's 2 into 9, that's 18, that's less than 20. So I can't just take 2 and 3. If I take a 3, I also have to take a 5 with it. Otherwise the factor will not be greater than 20. So if I take the 2 and the 3, with it I can take a 5, or I take a 2 and a 3 and with it I can take a 5 square. That gives me 2 factors with 2 and 3. Or I can take 2 and 3 square and with it I can take a 5. Or I can take 2 and 3 square and with it I can take a 5 square. Can I? No, because now if I take 2, 3 square, 5 square, that's the entire number 450 and that is greater than 200. So this one is also not allowed. So there's only one more factor I can take with 2 and 3 square. And now what's left? I don't take a 3 at all. Remember, I haven't considered the cases where I don't take 3. Let's look at that case. 2 into nothing for the 3's into 5. But I can't take 2 into 5 because this is also less than 20. But I can take 2 into 5 square. This is fine. So that's my additional factor. 2 into 5 square, 50. So totally there are 2 plus 1 plus this 1, 4 factors that satisfy the conditions. The answer is A. So you see again the prime factorization of 450 quickly allowed to list all factors that qualified. So we are done with number theory. We've looked at divisibility, factorizations, factors and multiples, quotients, remainders, prime factorization, and a host of problems involving these concepts. These are very popular among multiple choice exams because, well, they are fundamental concepts and you can ask really tricky questions with them that test understanding. There's not much knowledge needed, but a lot of understanding.